as we launch into this morning's discussions. We'd like to start with a land acknowledgement to honor local protocol and to express our collective gratitude to the Indigenous communities who continue to steward and to live on this land here and across the country, the places where all of you and all of us live and conduct our research. So as we begin our meeting today, I would like to acknowledge the Lekwungen people, also known as the Sanghees and the Esquimalt First Nations, past, present, and future, on whose traditional territory our conference is held. I'd also like to introduce myself for those of you who I haven't met yet. I'm Janet King, and I'm the chair of the board of directors for the network, have been for a few years now, started in the middle of COVID. So I actually hadn't met most people before being able to come to this AGM, and I'm absolutely delighted to be here and to actually meet in person many people whose faces I've only seen on the Hollywood squares of last year's AGM or the various meetings and webinars that we have. So it's just a pleasure. I've met a lot of you, and I hope to meet everybody before this is over. And I'm also learning so much from the presentations, the posters, and just all the conversation. I feel a real buzz in the room and out in the hallway as well, which is the sign of a good conference. So that's just great. And Stefan has a few comments now, particular to the conference.
Yeah, I do. Thank you, Janet, and good morning, everybody. It's such a pleasure to be able to see you all in an in-person AGM get-together, partners, students, postdocs, PIs, Northern Voices. You came very far to be with us here. And I just want to acknowledge some of those contributions because a network has many different parts, and sometimes we see the parts that we're in, but we're not aware of all the other parts that are needed to make it run. So I want to acknowledge the contribution of all the partners that we have from the beginning of even starting this journey, and the Northern Voices, both Indigenous and non-Indigenous, who have been helping to guide us as a collective in a way, broader than this network, and came here to exchange with us and also have a certain amount of passion and patience for, things sometimes working differently in different sectors and in different places. So really my gratitude for you doing this. The second group I want to acknowledge is all the students here and the postdocs and people like Omid and Nick who really do the research in the network and who also have to do the work of engaging with all of these different people, not everybody with everyone at the same time. But it's not that easy to actually live up to these expectations that we've set for us, because there's so many other things you need to do in your lives when you are a grad student. And so I really want to focus our attention on like acknowledging the efforts that went into it and the passion, and just kind of celebrating the research that's been done, and also acknowledging how that derives from everybody here somehow putting an investment into this network and into the success of other people rather than their own success, because that's the only way that this works, is the trust to say, I'm going to invest a little bit more than what I get out in a short term. And I hope from the buzz we're feeling, Janet alluded to that right here, and being in person and being excited about what's happening, I hope that kind of emphasizes and strengthens us in this approach. I also want to express my gratitude to Emma and to Bernard and to Tristan. I don't think anybody has an idea how much work it is to pull this off. And I'm just so impressed with this whole event. And I can't even begin to express my gratitude that, you're making this possible, that we can actually have these conversations in such a nice environment, and that everybody's here and everything's well prepared. So thank you very much for that. And then finally, I mean, we came together as a community in various ways 6.5 years ago to think about networking permafrost research in Canada. The CPA came out of this, a lot of different initiatives in this broader community that is a lot broader than PermafrostNet. And I think there is a need and a current trend to try and grow people involved in permafrost knowledge here. And I just want to share an experience that I had a couple of years ago at the European Permafrost Conference in Chamonix, where I was invited to a dinner with a bunch of old friends. And those were people who all did their master's or their PhD in an EU project in the late 90s. And so we were having dinner and everybody was happy to see each other. And at some stage someone said, look, there's like 10 or 15 profs in this room, or people who still work in permafrost in their countries. And it kind of hit us what the influence was of that network and of that community of people in the late 90s that carried on for decades actually to shape that part of permafrost research. And I hope that in 10 years and maybe in 20 years, many of you will still work together, have trusted relationships, maybe have a dinner together and say like, wow, look at how far we've come. And so in that sense, it really makes me happy that we're all together here in person. With that, I'd like to invite Tabatha Rahman, who's going to chair the next keynote session. And just to reiterate, why is this a keynote session? A lot of times we have kind of like older, experienced academics who give the keynotes, but we're here as a network interested in the research that the network does, the network students, network postdocs. So it's very fitting that the young people who do the research in this network actually set the tone for the day. And let's hear what they have to say and just celebrate their success. Have a nice day.
Good morning, everyone. My name is Tabatha Rahman. I'm a PhD student with Pascal Roy-Leveillé at the Permafrost Research Laboratory at Université Laval in Quebec City. And my first introduction to permafrost was about 6 years ago when I did Wayne Pollard's field course on Axel Heiberg Island. And since then, I've had the opportunity to work with and learn from a lot of you here in the room today. So I'm extremely grateful for the tight-knit permafrost community that we have here in Canada. So our next speaker of the day is Hannah Macdonell of Theme 3. Hannah is currently wrapping up her master's thesis at Carleton University under the supervision of Stefan Gruber. And today she will be talking to us about evaluating permafrost models under a range of accordance measures for different terrain units and for different temporal subsets. Welcome, Hannah.
Perfect. Hi, everyone. So my name is Hannah Macdonell. Thank you for that warm introduction. I can skip my title slide more or less, which is great. So we've heard about different mitigation and adaptation practices and how they can be supported by modeling. And I'd like to elaborate a bit on this. So modeling, I like to think of as an inherently heuristic activity, which is used to derive information regarding the severity, timing, and location of future permafrost changes at the local scale. So characterizing things like ground ice, the active layer, carbon content, and ground temperatures where direct observations are unavailable. However, it is important to acknowledge that there is significant variation in the predictions that are made by different models. And if we want to ensure their reliability and usefulness in climate change, adaptation, and research, we have to be able to establish trust in the predictions that they make. Unfortunately, there are some obstacles in the way we evaluate models. And so I'm going to talk about those today. And I've loosely categorized these into statistics and data availability themes. So these issues include a lack of consensus on one specific approach to model evaluation, the intangible nature of the values that we use that prohibits clear interpretation of model performance, both the limited spatial coverage and incompleteness of measurements that we use for model validation, and finally, the unfortunate discrepancy between what we are actually able to observe and what permafrost variables that we're most interested in. So the aim of my project was to improve the value of permafrost modeling outputs, and this is through providing an accessible software tool that would rigorously test model output and basically provide a ranking framework. And it was designed with some of these obstacles in mind. So in order to demonstrate a model ranking framework, you do need some models. So in order to demonstrate how the tool works, I developed and then evaluated ground surface temperature simulations, or GST simulations, at clusters of sites in the Northwest Territories. So produced different models for evaluation. I used 3 different data sets, meteorological data sets, shown on the far left, in combination with some the numerical model geotop. And I evaluated their individual outputs in addition to their ensemble mean. And so on the right, we see Acomatic, which is basically just the name of the software I wrote that implements the model ranking framework that I'm going to talk to you about today. So GST is no misnomer. It is, in fact, the temperature recorded just below the ground surface. And what we like about this variable is that it is not only highly representative of the underlying thermal regime, but it is also relatively inexpensive to measure relative to something more sophisticated like a borehole. So these maps are showing 3 different clusters of GST sites that I use to evaluate my model simulations. And we have sites around the Yellowknife municipality that are shown in blue there, as well as some 2 other clusters northeast of Yellowknife. So we have KDI shown in yellow and Lac de Gras in red. So in order to tailor geotop to each model of interest, what you can do is you use parameters. So on the right here, we see a rough drawing of which components of the natural system were used to generate estimates of ground temperatures, which for the purposes of this project included vegetation, snow collection, self-shading from surrounding topography, the drainage or terrain wetness at each location, and ground material. And this was done in part using high-resolution digital elevation model of the area, which is shown on the upper left, these black and white images. And so there are 3 maps just showing the differences across the 3 different clusters. I then used this information to estimate site-specific characteristics such as water drainage, self-shading, and concavity. And concavity can be used basically to estimate snow distribution across the area, which is just used in the absence of field notes, which were used to identify things like ground materials and vegetation. And so at the end of this, I had a whack ton of temperature simulations for these locations. And this time series data is then fed into the ranking framework, which was designed to account for all of these obstacles that I mentioned previously, and we'll now cover in a bit more depth. So to start with, the first being a lack of statistical consensus on which metrics that we should use to summarize model evaluation. And that means that we end up with a bunch of different numbers to summarize model performance and often no clear way to compare them. The choice of metrics can depend on factors such as interpretability, biases, or reliance on large data sets. And different measures have different strengths and different limitations, which can make them more or less useful for a specific application. And even common statistics such as root mean square error, Pearson's coefficient, or bias, which are frequently used, are unable to fully capture the nuance of model deviation in isolation. So it's essential to select summary statistics that are best suited to the characteristic of a predicted variable, which in my case is ground surface temperature. And by doing so, you can ensure a more comprehensive assessment of a model performance. So while the software tool that I designed is able to support any summary statistic that is suited to a time series variable, the metrics selected for this application included a mean absolute error, Wilmot's index of agreement, and a bias metric. So the second issue of statistical values is that they are relatively intangible in reality. So you cannot hold an index of agreement in your hand. It does not exist. They also lack units, dimensions, and can often be mathematically unrelated. And so if we want to improve our understanding of relative performance, we want to maybe dilute that down into ranking. So on the right here, we see a figure of a rank distribution. So we're looking at how models basically ranked across 4 different relative to each other. So on the top left, you have 0, our ERA 5 model ranked 0, or ranked first no times kind of thing. So you can see a distribution of how your models perform. Another issue I wanted to highlight or to address in the ranking framework was the already limited nature of observational data. So to ensure unbiased evaluation of model results and to avoid introducing seasonal biases, complete years of data are often preferred during the evaluation process. But this approach leads to significant amount of data that are excluded from evaluation of the model, which you can kind of see in the leading and trailing patches of red. In order to address this issue, the ranking software employs a bootstrap procedure, which first divides the modeled and observed time series into these month-long segments, and then randomly samples from the segmented dataset for each month of the year, which means that leading and trailing months can then be used without influencing results. In the end, you get this really nice picture of distribution of model performance for each month of interest, and then that can be aggregated to contribute to your overall rank. Ground temperatures are primarily controlled by climate, but the microtopography, local surface features are what controls the extent to which these climate signals will attenuate with depth. This plot on the right shows a very high degree of spatial variation in ground surface temperature, and this is just a small set of the observational data that we have that I wanted to use to show how different terrains can respond to similar driving climates, just given differences in their drainage, vegetation, shading, and snow. The problem here is that the Canadian tundra is incredibly heterogenic, much of which is underrepresented. There's not a whole lot we can do about this, especially on a master's thesis timeline and budget, but what I implemented in my model analysis and subsequent ranking framework is that I identify and subset model performance by terrain type. So this means we can better understand not only how our model performs in different environments and be transparent about limitations, but once again, removes kind of bias introduced by locations for which you might have more data. The last portion of my project is looking into how our model ranking framework extends to other variables. So we have this issue where the variables that we have lots of observations for, such as ground surface temperatures, are not actually what maybe we're always most interested with respect to permafrost change. So things like thickening of the active layer or ground ice content we don't have as much data for. So using the ranking software, I measured to the extent to which model performance at the surface differs from performance at deeper depths. For example, we see what the extent of the distribution of model ranking shift with depth, either for better or worse. Here on the left, we see the differences in ranking here on the left, we see how well a mean absolute error correlates with depth with using GST and measurements at 5 meters or 1 meter depth. Some future work I envision for this project includes looking at how this method could be tailored to other variables of interest and applying this method using different modeling software, so things like Classic or FreeThaw 1D. In summary, I would like to encourage you all to consider how these solutions applied today might work for your own modeling projects or whatever it is that you do. Every modeling application is unique. There is no one-size-fits-all, and I would be interested to hear everyone's thoughts on suggested practices over the next few days. Thank you very much for listening. Thanks.
Thank you, Hannah. And Hannah has a poster in the poster session. Okay, so our last speaker of the day is Galina Jonat, who is also Thum 3. Galina is working on her PhD at Carleton University with Stefan Gruber. When she's not working, she enjoys Nordic scuba diving, which she says has prepared her for work in cold regions. Her PhD focuses on modeling future permafrost thaw, and today she's going to be telling us about how to prepare climate model data for local scale modeling of future permafrost thaw. Please welcome Galina.
Hi, good morning. Thanks, Tabatha, for the introduction. I'm sorry I was the only one who submitted a fact. I shouldn't have done that. Anyways, good morning, everyone. How does this work? Okay, cool. So yeah, as Tabatha already alluded, I'm a third-year PhD student in Stefan Gruber's lab, so the same research group actually as Hannah. So actually, you will see in our presentations there are some parallels as in how we approach our modeling of permafrost thaw, while I focus a bit more on the future. But first of all, I thought I should think about why we actually need to simulate future permafrost thaw. And this doesn't just concern the future, but also kind of the present, and just wanted to build up the case for modeling in general. So the first point is models can complement observations in a lot of ways. The most obvious one is probably the spatial coverage. So we all know, like a lot of people have been in the field. we don't always have observations that kind of cover an entire area. So by kind of using modeling, we can extend observations for both time and locations where we don't have observations available. We often also have the problem that when we have observations, we can't always go back into the field every year or like maintain our observation sites. So as Hannah already said, there are often gaps in the data. So kind of filling those in can actually be quite valuable. And the third big point where models can complement observations is that we can look at variables that are actually very interesting in the context of permafrost change, as a, like just like ground ice content, changes in ground ice content, and ground subsidence, for example, which is a big thing when we think about permafrost hazards. And then kind of going on from that is actually building the case why we can't just use climate models to derive what's going to happen to permafrost thaw. Because when we think about like the global climate models that we see in like the IPCC report, the Intergovernmental Panel of Climate Change, I always do that wrong. They are more concerned, like those models are developed on like large scales, and they're actually most interested in also large scale impacts of climate change. So for example, in the role of permafrost, it's more like, okay, we can look at what is the role of permafrost when we think about the global carbon budget, for example, rather than focusing on what we see here in the bottom, which is kind of, oh, what's happening to my road here? So this is kind of where I want to come in and kind of make my contribution, just to kind of set the frame for this whole situation. So I'm just hoping to walk you through the whole thing as good as I can. So this is kind of the processing chain that is going from the big climate model to data that we can actually use to force our permafrost models. And the top part, like the brown parts, are basically very much concerned with what questions we're asking, kind of what do we actually need, what type of information do we need for permafrost, and that, yeah, depends on the question. I'm going to focus on the bottom part that is in the little box here, because the fact that how we prepare that data is actually the same for all the questions that we're asking, and the decisions that we make. And here we have a few challenges that we want to address. So the first challenge is the spatial resolution of climate forcing data. So if we think about, again, global climate model data, it's often just at a resolution of 100 kilometers, which is kind of the big yellow box that you can see here. And I think I tried to check for like a local reference, and I think that's actually the entire island of Victoria. So if you think about like the climate or the weather is not the same for like the entire island, just for reference. At the same time, when you try to correct that for a local scale, the best guess of reference data, because we don't have a weather station at every permafrost site that we're interested in, we actually need to use reanalysis data that Hannah already mentioned, downscale that to like a point scale using some fancy tools. And that is what we actually use as our reference data to then downscale the big global climate model to our local scale. So this is basically what is depicted here. Excuse me. So we're using this downscaled reanalysis data that Hannah has tested, and then kind of feed that into the biasing algorithm, which basically corrects for incorrect parameterizations because of scale issues and low resolution to kind of statistically match our reference data. So what would that look like? This is basically the outcome of it. So in the bottom, I guess it would be left. So the orange and the blue, you kind of see the original climate model in blue, the distribution of air temperature, just like a simple histogram, compared with the reference data that is in orange. And by actually performing the statistical correction, we see that we can actually align those statistics to our locality, which is what you see in the bottom right. Another strength of the debiasing method that I am using is that it also corrects for the relationship between variables. For example, when you think about the relationship between temperature and precipitation, we know that warmer air can hold more moisture. So kind of correcting for that type of dynamic as well. The second challenge that we have is the temporal resolution of the climate forcing data. So the global climate model data that we actually get from those big modeling efforts are on a daily basis, but to force our permafrost models, we actually need something that has an hourly resolution. So for that, again, I was lucky enough to be recommended another tool that kind of extracts a sub-daily profile for each single variable in that same season, at that same time of the year, and then applies that profile to generate hourly data from our daily means. And the third challenge that we have is a bit more harder, I guess, to wrap your head around, because we want to also then decide which models are actually doing well at representing our local climate dynamics. Maybe there's some climate models that really don't fit at all, and we don't want to introduce that type of bias into our permafrost modeling approach. The challenge here is that climate models actually, again, they don't really care if a certain temperature is reached on January 1st or 10th or 20th. They more care about like the large scale dynamics and long-term trends of the climate variables, while weather data that we have for comparison capture short-term and variable conditions. So one way to work around that is actually, instead of kind of comparing each variable one by one and day by day, is looking at the large-scale statistic. And one way to do that is actually by looking at how well the correlation, again, is represented between the variables, which is what you see here. And just to kind of point out the strength of the method used, is that, so we have this whole set of variables, and what I basically did is I calculated a correlation matrix, so kind of how temperature correlates to precipitation, to solar radiation, all these kind of things. And I looked at how well is that represented comparing the original climate model with the observation correlation and the corrected climate model compared with the observation. And that's what you see on the right-hand side, is that actually the error in which we represent that correlation is actually much lower, which you can see that is much paler actually. So I'm very happy with that type of result. So the next steps will be guided by the question of how we actually kind of elaborating more on how we can compare and select driving data that best represent climate in our target area, and then kind of extend such that we have a bit more confidence on extending that into the future. And then, I mean, one of the key questions will be in the context of permafrost modeling is actually, is that selection that we make something that looks really good when we compare the atmospheric side of things? Does that actually translate also to a good performance on the permafrost modeling side of things? And like, again, thinking about a lot of different permafrost variables and thinking about how we compare them more statistically instead of comparing one by one. And I think that's all that I had for you today. So thanks. Any questions? Comments?
Thanks. I just have a comment. That's a lot of work. And as somebody who spends time thinking about putting climate data into our models for like a geotechnical side of thing, thank you for taking the time, because it's going to really inform our models and what the best practice is going to be for using that climate data. So yeah, to you and Hannah, thank you guys for the work you're doing, because we just want to like use a model to find some answers. And so we appreciate that you're spending time thinking about the models and how to do well. Thank you both.
So just wondering, like, so these biases, so what's your idea where they are actually coming from? Is it just like a scale thing that the models are much?
So I mean, there are a lot of biases that are connected with climate models, right? Because we also have that kind of scenario bias, and we have like bias that, I mean, models are never gonna be able to represent reality. It's just the best guess that we have. But the bias that we can reduce is that type of systemic bias, which is concerned with like incorrect parameterizations of certain dynamics. That is the part that we can correct. There are some other biases that are included in climate models that we don't really have a chance to correct.
It was probably part because I didn't pay attention there, but so what wasn't clear to me whether these models that you apply, whether you apply them to very small spatial scale, so that bias is
yeah, so
taken out.
Exactly, so that bias is kind of taken out. Okay. So like kind of, it's almost, you can think of it like in this context, it's basically part of a downscaling process. Yeah.
So thank you so much to our three speakers. They all have a poster, so feel free to go continue the discussion with them later on. So I guess now we're on to our coffee break.